Hello, dear guys. In the ITB International Geothermal Workshop 2021, I would like to make a presentation with the topic Reservoir Dynamic Monitoring in a Liquid-Dominated Geothermal Field based on the tracer flow test method. I would like to thank to my mentor and colleague, Heru Birian Pratama, Ali Asad, Sutopo, and Abu Dawud. This is my brief outline on my presentation. In the first three, in the beginning, introduction, methodology, and objective. In the middle session, we'll talk about TFT monitoring and a geothermal field condition under study. In the last session, I would like to talk about reservoir dynamic in the study field, experience with injection breakthrough and steam cap development, and last but not least, conclusion. The exploitation of fluid from a geothermal field will affect a dynamic change in the reservoir. In a liquid-dominated or tube-based geothermal field, two common impacts. The first one, decrease in the performance of the producer, which experience injection effect, named chemical breakthrough, or in the long period, thermal breakthrough. And the second impact, because of exploitation, is lowering in water level in the reservoir. As a result, a shallow steam reservoir appear and expand over time. How to observe the dynamic change is by monitoring enthalpy. One of the technique is using tracer flow test method. Tracer flow test method is under comprehensive surveillance program, need to be implemented along with the NCG and steam and chloride in brine monitoring, and so with subsurface PT monitoring. The methodology in this study first is by select a liquid-dominated geothermal field which has long history, implement comprehensive surveillance program. Got the access to the Geosan reservoir database, the enthalpy from TFT, chloride in brine, NCG and steam, and also subsurface temperature logging data. And for those data, conduct analyze comprehensively. To get the objective of this study, which is observe injection breakthrough and steam cap development, and give some input in the reservoir management to have a better operation. Let's look a brief about the TFT monitoring. TFT measurement method of steam flow rate and water flow rate and total enthalpy of two fluids, base fluid produced from a geothermal well. The totality of the mixture can be calculated using a simple heat and mass balance equation. This is the equation. And the simple formula also can be applied for calculate the mass flow rate of water, and so with steam mass flow rate. How the TFT technique applied in the field basically is divided in two parts. The first one, in the injection side, we have inject liquid tracer along with gas tracer via a TFT unit through a injection port near the wellhead. And in the downstream side, after we have a mixture completely the tracer into the fluid, we take a sample using a mini separator. And after that, all the sample sent to the lab to have a calculation of steam and brine flow rate and so with the enthalpy. Two methods of TFT be recognized. The first one, US development by Thermochem, basically using SF6 as steam tracer and kind of naphthalene in the liquid tracer. The second method developed in New Zealand by Brian Lovelock is using isopropanol steam tracer and sodium benzoate as a liquid tracer. The enthalpy measurement from TFT is relatively accurate. 3% difference compared with the orifice measurement. And the TFT monitoring already become a routine periodic program in many liquid-dominated or two-phase geothermal fields in the world. In Indonesia, Salak, Hulu Lahindong, and in Philippines, Tiwi, Bulalo, and Southern Negros. Let's look into the geothermal field under study. This is a liquid-dominated geothermal field that the reservoir is relatively neutral and benign and with low to moderate gas content. The upflow zone is located in the west sector of the production. The reservoir flows to the northeast, to the east and southeast, appear in the surface as surface manifestation. Based on the subsurface structure, fluid chemistry, PT reservoir, and the tracer test, this field can be divided in the 4 production cells: west, central, east, and far east. In all active production here, we conduct enthalpy monitoring every 3 months, chloride in brine, steam, and NCG in steam every 2 weeks, and so subsurface temperature logging data every 1 to 3 years. As stated in some paper, in the west sector, causing by impact of brine injection, and so with condensate injection will already affect significant effect in 8 wells. The brine effect will create the chloride increase, and never the condensate injection dominant cause the chloride decrease. And in this east sector, many well experience with steam cap development, creating relatively high NCG in steam relatively compared to steam from liquid flash, 1.5 to more than 2.35%. Let's now go into the detail reservoir dynamic in the field study. First, we have to look in the west sector, there is a significant amount of brine injection from this area And so with condensate from this area and later on move further to the west. Two well as an example showing the changing is the reservoir. The first one is P1, relatively have a deep entry, get impact from the injection from the west. And the second one is P2, the entry relatively shallow. Let's go to the more detail. P1 well that's experienced with injection breakthrough. The surveillance data show the enthalpy decrease from 1100 to 1000 kilojoule per kilogram. The temperature measured decline 275 down to 245 degrees centigrade. The NCG in the steam quite low, 0.1 down to 0.05 with percent. The chloride decrease in year 1 to 8, mainly caused by condensate from 812, more significantly compared to brine from A9. But after the condensate move and stop further to the west, the chloride become increased as a effect of brine injection from A9. In P2 well, experienced with steam cap development, the enthalpy of produced fluid indicates steam, 2800 kilojoule per kilogram. No more brine, only steam. The measured temperature in the entry decreased 220 down to 210 degrees centigrade, creating NCG in the steam relatively high, 0.5 up to around 5 weight percent in the steam. The conclusion, first is the reservoir dynamic can be observed whenever compressive surveillance is being implemented and should be as a multidiscipline monitoring such as enthalpy using TFT, NCG in steam, chloride in brine, and so with subsurface temperature data. And by understanding a better reservoir dynamic, a management process or injection process can be improved so that the electricity generation using geothermal fluids in a geothermal fluid can be optimized until the end of the contract. Some recommendations being inputted. The first one, continue to implement surveillance program covering multidiscipline monitoring. Second, anticipate the adverse effect of temperature drop in the liquid reservoir due to injection breakthrough. And the third one, regulate producer that experience steam cap formation so that not to exceed the NCG tolerance limit in their power plant. I think that's all my presentation. I hope my presentation can give you a benefit in your career or interest. Stay healthy, full of joy. Thank you.
Hello everyone. Hope everything is running well with us and may God always protect us against COVID-19 outbreak, and don't forget, please keep stay at home. We are from ITB, which is supported by PT DFI, PT Sustrako, and Geodipa Energy to present one of the geothermal issue in this ITB International Geothermal Workshop 2021, with taking a subject of technical analysis and feasibility of the scale removal in the geothermal well and surface production facility by using true fluidic oscillator or TFO pulsating wave method technology. As all of us aware that scaling is the most classic problem or commonly found in the geothermal industry, since it could deplete the electricity production and increase the maintenance cost. As we know that the scale types is a carbonate mineral, calcite or aragonic, amorphous silica, metal oxide, and sulfide. But the most common geothermal scales are silica and calcite. The scale deposition process normally will found on the geothermal well, geothermal power plant, and geothermal reinjection line. In this discussion, we will more focus on the geothermal well. Scale deposition process occur in the production zone, inside production casing, or mostly is founded at the liner hanger. So please see the picture. This is the area of the liner hanger, and then in the flow line, and also at the behind of slaughter liner or near wellbore. We have many mechanism how to remove the scale, but normally the system is only remove the scale inside the casing. We know that with the mechanical, we could mill and broaching the scale out, or we use a water jetting or the chemical. But the problem is how to remove scale allocated behind slaughter liner or outside casing on this area. In this presentation, we would like to introduce one of the solution system to remove scale allocated behind slotted liner or near wellbore. The system is called TFO, True Fluidic Oscillator. Actually, TFO system has been used in many years for oil and gas well application, but not common in geothermal well application. The true fluidic oscillator is controlled by a fluidic switching tool to divert fluid flow, and the flowing will be frequently and create what we call a pulsating pressure wave. And the most important thing that in the system with no mechanical moving part. If we see in the picture, this is the concept of the FO. Once we pump the fluida in the system, and then they will divert by two. First cyclist will be in this area, and then the second cyclist will be through in this another area, or we call switching. In this picture, will explain us is differences between jetting or the jet deflection and load switching. In the jet deflection, once we pump fluida, and then the another agent will put more power to the fluida and then become jetting effects. But in the load switching, once the fluida pump in the system, and that another cyclus will be go to another way. So mean that it will be switching in very fast in microsecond. So once we run the TFO, please see on the picture, then they will create the pulsating pressure wave. The TFO pressure streaming wave could able to remove scale on this area on out of slotted area, and then also they can streaming out, spread out inside to the production zone. So meaning that in this area will be clean out of the scale. The TFO pressure wave streaming that lead the physical disruption of the damage of the scale in this production area. TFO pulse wave cleaning mechanism actually could divide combined by three cyclic loading, acoustic streaming, and chemical reaction. In the cyclic loading, the stress loading caused by the oscillating pressure wave as the tool is reciprocated through the interval. So meaning that the cycles of the wave or streaming, the pressure streaming wave will be back impact to the scale oftenly or frequently. And then the second one is acoustic streaming. We call a pinpoint placement of the treatment fluid right to the target area, meaning this is little bit like a jetting effect. So the fluida will direct attach the scale and then crush them. And then the next is a chemical reaction. So meaning that we can put additional chemical to make more enhanced or more effective. Normally, we run tap oil by fresh water, so it will be reduce our cost. This is the picture that will show us since the TFO is applied, and then the scale will be break it out and then pump it out. This is a video will show us how the stream is created. So once the TFO is pumped, and then the streaming wave will be separated out to the 360 degrees area. The bottom hole assembly. This is the bottom hole assembly for CTU application, coil tubing unit. We could see that we use 1.25 inch OD TFO for coil tubing application. This is a very simple BHA. They could connect direct to the CTU unit. The another one is BHA for drilling, rig drilling. So we use 1.5 inch TFO. This is for rig jointed pipe. So mean that if we use a drilling rig, then we can use this application. So we put also tungsten down in the tool to protect the tool against the rest of scale if we run the tool down to the bottom. So they will protect the jetting or the tool of the FO itself. The most important of this concept that the FO pressure pulse wave is not limited by stand-off or hydrostatic limitation. This is very effective in large diameter hole. Now we discuss about pressure, pulse, and force. Basically, we use a formula based on Newton second law. So the Newton second law said that F equal to M times A. F is a force, M is a mass of the volume of fluid ejected per pulse, and then A is a difference between the exit velocity of the fluid from the oscillator minus velocity of the fluid in the well bore below the tool at the same pump rate. So in the test state, we show that 1.5 ODTFO will create 190 hertz. So meaning that in 1 second, it will be create 190 time frequency of pulse. And then if we go to the 1.5 inch ODTFO, it was measured at 175 hertz. This number is very ideal number to create the TFO once we pump fluid through the TFO system. This frequency were stable. Increase the pump rate did not have any appreciable effect to the frequency. It means that when we already reach the optimum frequency, then when we put another flow rate, it will be change the frequency. The pressure drop of 1300 to 1400 psi across the tool was measure the activation rate. The testing was performed at Slumbersea Laboratory in Robertson, Texas. This is a very big pressure drop that will effective to create the very powerful of this pressure wave. This is picture will show us that when we pump only with limited the flow rate, then the fluid will not affect, will not create the fluid oscillation. But when we pump with a certain barrel per minute, we have calculated, but with the 1 barrel per minute, they will optimal oscillation of 200 hertz will be reached. This operating is using coil tubing unit. So this is the calculation. It is simple. So once we pump 1 barrel per minute, it will be create the power or the force equal to 106 Newton. Could imagine that this power is very big. We have some case history. The first history is TFO treatment for 10-in injection flow line with barium sulfate scale up in Illinois, USA. This is the flow line full of scale, and then this is a before treatment, and then this is after treatment. You could see that it's very clean inside the pipe. So we can show you how to TFO working. Once we pump TFO and then create the streaming wave, and then the wave will be attack or crush the scale inside pipe and pump it like a powder. This is very effective for the long flow line. And then another story is a TFO for oil and gas well application. This table shows us that once we treat the FO, then the production will increase. So we can see that some well increase 76%, until 12%, until 39%, 64%, and also we also get the 400%. This is also for the gas application. So all looks that the number will increase once we start the FO application. This is another story that we would like to discuss, that FO is also being used for Dieng geothermal well. We have a sample for geothermal well number XXX7C. This is the different, we put the different name because of confidential issue. So hope that it can give us the more picture how the TFO working for the geothermal well. So the well triple XC was start produced in 2007 with an initial capacity 11.3 megawatt. In 2010, the production capacity was dropped to 5 megawatt, and they did a walkover and capacity up to 8.5 megawatt. After that, the, the well significantly dropped to 3.5 megawatt. So we put the FO and implemented it there. So the production increased from 3.5 megawatt going up to 10.6 megawatt initial capacity. So we can see on this table. So this table is a total megawatt gross from 3 well, number 7C, 7B, and 28. So when the production dropped to 17.2 megawatt, we did treatment in 7C, and then the production increase become 27.8. And once we also apply this TFO for 7B, the production increased to 33 33.6 megawatt. This is very interesting technology that we could apply more in Indonesia for geothermal application. The conclusion, the TFO treatment technology is one of proper scale removal technology alternative and feasible to be applied in the geothermal industry. The system can use this descaler, chemical, or fresh water to dissolve and remove scale in the wellbore or in the surface facility. The beneficial effect of the whole cleaning energy generated by TFO are first, the TFO pressure streaming wave could able to remove scale out behind the slotted liner casing production or near wellbore. Number two, the TFO pressure wave that lead to physical disruption of the damage of scale in the production zone. The TFO fluid flow induced by pinpoint string. And then next, the enhancement of chemical reaction through greater surface contact area. And then the last one is the TFO system with no non-hole mechanical moving part could able to generate by drilling rig, SW, CTU, or by other lifting equipment, reckless such as crane, of course, have to be modified by using 238 macaroni tubing. I think this beneficial will cut our production cost significantly. Your kind attention will be greatly appreciated, and please take a look our paper for more information in detail. And please feel free to contact us if you have any question. Thank you. Bye.
Hi everyone, I'm Fritz Monterozo, Geothermal Technical Lead from Nalco Water and one of the authors of this technical paper entitled Recovery of Reinjection Well Capacity Using Online Scale Dissolution. My co-authors are Jean Robbie Gika from Energy Development Corporation and Dinesh Mantri from Nalco Water, India. I would like to take this opportunity to thank the organizers of the 10th ITB International Geothermal Workshop for allowing us to share this technical paper. The main goal of the study is to assess a potential treatment for the recovery of the capacity of a scaled reinjection well. So we have conventional methods available to us, like mechanical workover and bullhead acidizing. So we want to explore a method that can help recover capacity without putting the well offline. So if this method will be deemed effective, this can be an economically viable alternative with respect to the conventional methods, also carrying out the recovery at a much reduced complexity and lower risk in terms of safety and asset life. So as you can see in the dissolution setup, we are taking advantage of the flow of the brine into the reinjection well to deliver our dissolver. So this will target existing scales upstream of the well and downhole. So the dissolver Geo991, as you can see here, it is an alternative chemistry to commodity acids. So the active component is an acid salt that has the potency of 10 times of hydrochloric acid but has lower corrosion tendency. So this active component complexes with existing silica scale, which helps in increasing the porosity of the scale and eventually dissolving it. So the online dissolution evaluation is divided into 3 stages. So we have the laboratory dissolution test, where we assess the susceptibility of the target scale against our dissolver. Aside from the lab dissolution test, we also have the side stream test, where we are assessing the dissolution or assessing the performance of the chemistry at near field conditions. So after getting sufficient data to increase our confidence that this will work on an actual well, we are now ready to deploy an actual field test. So prior to conducting the dissolution test, XRF and XRD analysis were conducted to determine the identity of the scale. So for the lab dissolution test, we soaked the scale samples in varying Geo 991 solutions and observed both physical and chemical evidence of dissolution. So the representative scale that was used for the side stream test achieved 76% dissolution. The representative scale, on the other hand, for the actual test was able to achieve 100% dissolution. So for the side stream test, as you can see, a scaled alveolus pipe was used to represent the scaled downhole conditions. So a small portion of the brine was diverted into the side stream setup, as you can see in the upper right figure here or image here. So so a small portion of the brine was diverted into the side stream setup where it splits into dosed and undosed lines. So the goal of the side stream test is to check physical and chemical manifestation that dissolution is happening. So the lower right images here are the actual site conditions where we conducted the side stream test. So here is the scaled alveolus pipe that I mentioned. So both alveolus pipe are present for the dosed and the undosed lines. So the pictures on the left side show the dosed and undosed conditions. So the upper photos were the side stream test, and the second set of photos were after the pull out. So as you can see, the dissolution was more pronounced in the dosed line. So this particular scaling scenario, so this one can be considered as a worst case, considering the hardness and how the scales was and how I mean the scales on each alveolus pipe. So they are quote unquote already baked inside the pipe. So the third set of photos show the the third set of photos shows the pipe holders for both the dosed and undosed lines. So as you can see, the dosing helped in minimizing the formation of new silica scales, and this can also be observed in the mini silencers. So mini silencer section that we have here. So the fourth set of photos. So after decommissioning, it was observed that less silica deposits were seen in the dosed line compared to the undosed. So the prevailing modes of action of the chemistry is to dissolve existing scales and to prevent new scales from forming. So the dosing regime involves a shock dosing phase, which lasts for 12 to 24 hours. So targeting pH of 3 to 3.5, and the dosage will be further reduced to a certain level where the prevailing pH is 4 to 5 for 6 days. So this is true for the side stream test. So as expected, the corrosion rate is higher during the shock dosing phase. But considering the amount of time and the projected corrosion rate or the metal loss, so it is negligible. So it can also be observed that the monomeric silica levels were maintained for the dosed line, which validates the prevention of new scales. So in the actual field test, the main key performance indicator is the flow rate recovery or the flow rate level. What the team did differently this time for this test is to extend the period of dosing and use a carrier fluid that is devoid or has minimal silica levels. So for this particular test, we used condensate. So the target well has a starting flow rate of 4 kilograms per second, and during the first online dissolution phase, we were able to achieve 10 kilograms per second after 33 days of dosing. So consuming approximately 2,000 kilograms of the dissolver. So the dosing was stopped, but the well was continuously being utilized as a condensate injector. So we observed that the flow rate is still improving, even after Geo991 dosing, achieving 14 kilograms per second. So with a limited amount of condensate available, so the team decided to do an injectivity test to determine the actual or the final improvement prior starting the second phase of dissolution. So after injectivity test, we were able to achieve 26 kilograms per second. So since the starting flow rate is already high, we can expect that the amount of the chemistry that will be consumed is also high compared to the first, also higher compared to the first online dissolution phase. So after 16 days of dosing and consuming 3,000 kilograms of the product, we were able to increase the flow rate from, 235 kilograms per second. So this is also the original well capacity when the well was drilled. So aside from the flow rate measurement, ultrasonic thickness gauging was also conducted to ensure that the thinning rates during the actual run are within the acceptable limits. So in summary, the evaluation of this new method was done in 3 stages, with each stage aiming to increase the technical confidence to proceed to the next stage. So lab dissolution tests and side stream test results were valuable in carrying out the actual field test. So the commercial run results has proven that this new technology can be a valuable and a viable replacement for the conventional methods available today. So the use of Geo991 coupled with injectivity test was able to yield a final flow rate of approximately 35 kilograms per second from the initial 4 kilograms per second. So also the use of low silica fluid as a carrier of the dissolver can be beneficial in achieving better flow rates. So this method is worth considering for declining wells and scale composition similar to the subject RI wells and for those showing promising laboratory dissolution tests. So this ends our presentation. On behalf of the authors, we would like to express our gratitude for this opportunity. Thank you.
Hello everyone, my name is Dawud Hidayaturrobi. I'm from Star Energy. Today I would like to share my paper about AWI-4 comprehensive well evaluation for successful well intervention program. I will start my presentation with Salak field introduction. As you may aware that Salak geothermal field is located 60 kilometers south of Jakarta on mountains area ranging from about 950 until 1500 meters above sea level. Currently, Salak is the largest geothermal field in Indonesia and the 6th largest in the world with installed capacity of 377 megawatt of electricity. In the left picture is showing the NCG content profile from 3 power plants in Salak, unit 4, 5, and 6. So based on the picture, we can see that Salak field has been experiencing high NCG issues since year 2000, when some of the eastern well produced steam with high NCG content ranging from 2.5% until 6% of weight. It then continued in 2003 when one of the well AWI-4 produced steam with the significant NCG content above 10% of weight. And the situation finally caused the Unit 4 experiencing several generation losses since mid-2011 due to the high NCG content in the power plant above its maximum GRS capacity. Let's talk about AWI-4, one of the key factor in managing NCG level in the field and also in the power plant Unit 4. So AWI-4 was drilled in 1996, then redrilled in 1997 and successfully put on production in 1998 with initial steam rate 200 kph and brine 800 kph. This well was then readied again in 2003, but this well could not be put in the system due to very high acidity content above 10% of weight, as you can see in the right picture. So based on 2012 SG interference evaluation, it was indicated that AWI A-4 has the strongest connection to surrounding high NCG wells. So that's why this well was decided to put on venting or keep discharging to the surface. And unfortunately, in 2014, scaling was observed inside the wellbore of AWI A-4, and the situation caused NCG increase in surrounding wells, including Unit 4 power plant, due to the NCG interference effect from AWI A-4. Well, Brooklyn Out was conducted at AWI A-4 in 2015 using coil tubing unit with rotary jetting or rotojet method to remove the scale inside the wellbore, but it failed and causing another problem, which is wellbore plug. And this wellbore plug caused severe impact to the steam supply in Salak field, reduction of steam by 250 kPa or about 15 megawatt. And AWI A-4 wellbore plug condition was then reinvestigated for the further repair program in order to prevent a similar failure from 2015 operation. Then we use the company's well management process that provide us a guideline to do the comprehensive well evaluation through interrogation of multidisciplinary data. And this comprehensive evaluation use several data such as drilling data, production, the whole survey, and also the geochemistry data. The left picture is showing the illustration of AWI A-4 wellbore condition. So any data that we obtain with SAS will be shown later on in the illustration of this wellbore. So we will start with in the beginning of this well. During the drilling 1996, PLC was observed in depth to 166 feet. We also observed no cement return during 13 3/8-inch liner cementing, which indicating no cement at liner hanger, or the cement did not fully fill the annulus behind the casing. Based on the report of the radio operation in 1997, we experienced obstruction at depth 1621 until 1650 feet, then reaming out with 12/4-inch bead. Based on 2003 radial operation, we experienced several obstructions also at depth 1048 feet and 1254 feet, then reaming out switch and milling. We also observed the historical of wellhead pressure of AWI A-4 during the venting operation, and we observed that the wellhead pressure gradually decreased in mid-2011, suspect due to the flow restriction inside the wellbore. And we tried to investigate by conducting the PT shut in 2013, and we observed wellbore obstruction at depth 3,146 feet, and also liquid level above this obstruction at depth 2,500 feet. And we continued with the whole sampling of survey in 2013, but we failed to get a sample of fluid. Then we continued another survey, the whole survey, which is scale catcher, and we successfully obtained a scale sample with majority content of quartz, about 91.5%. To confirm the scale, we conducted the whole video in 2014, and we observed clearly scale image based on the whole video survey. Then we continue with 2014 caliper survey, and based on the data we got, there is indication of casing deformation at depth 1200 and depth 1600 feet, which is consistent with what we observed based on the drilling report in 1997 and 2003. And after that, we tried to remove this scale using the injection simulation method in 2014, but we failed. We tried to continue removing the scale inside the wellbore in 2015 using scale breaker method, but it also failed. And finally, we conducted rotojet clean out in 2015 to remove the scale inside the wellbore, unfortunately, it failed and caused wellbore plug, as I mentioned earlier. This wellbore plug indicated by liquid buildup until the surface. And we continue the investigation again after the failure of rotorjet operation in 2015 by conducting the null video in 2016 to get the image, but unfortunately we could not get the clear image from this null video due to the turbulence condition inside the liquid. But we also observed small heat flow at the bottom of the obstruction. Interestingly, based on the pressure temperature shut-in data that we conducted prior to the whole video survey in 2016, we observed a cooling temperature profile at depth 1590 feet, which is very close to the depth that we observed casing deformation based on the caliper survey in 2012. Based on this information, then we continue to reconduct the caliper survey again in 2016 to look at the latest casing condition, and we found the casing hole profile based on the caliper survey at depth 1600 feet. And based on this information, we continue to investigate the situation of Awi-4 wellbore by conducting scale catcher in 2016, and we obtained sample of mixed swelling clay with scale with smectite content, which was not observed on the previous scale catcher program in 2012. Then we continue to investigate this wellbore situation Awi-4 by conducting the downhole sampling in 2016, and we successfully got the sample. And based on the lab analysis, the fluid is content is diluted with chloride, which is indicating the crude influx or marginal recharge coming into this well. Based on the data that we collected, we assessed, we summarized into three important messages. The first one is the MR fluids confirmed by the fluid sample in 2016 flowed through the top of the feed zone and caused scale deposition that occurred starting in 2011 at depth 3146 feet, which finally caused the flow restriction, which confirmed by the well pressure vetting profile. Number two is the radial operation caused the casing deformation at depth 1600 feet, confirmed by the drilling report and also the caliper survey in 2012. Meanwhile, the rotorjet operation clean out 2015 has created severe condition, which is the casing hole at the same depth 1600 feet, confirmed by the PT shut-in data and also the caliper survey data in 2016. And this casing hole has allowed the smectite from clay cap falling into the wellbore, then mixed with the scale plug, plugging the wellbore of Awi-4 at depth 3041 feet. Based on that evaluation summary, a scale clean out program was developed in 2017, and then we used an improved method of rotorjet to try to open the scale plug inside the wellbore of Awi-4. And finally, this improved method has successfully open the scale plug and finally able to reduce the unit 4 NCG content down to 1.3% of weight. And with this situation, we added steam supply about 670 kps or about 40 megawatt in Salak feed within safe operation in unit 4 below the NCG content limit. As the conclusion, Awi-4 is one of the key factors in managing the level of NCG content in several wells that affecting unit 4 NCG content level. Comprehensive evaluation of Awi-4 wellbore condition provided a better illustration in developing proper method in removing the obstruction or scale. And the successful clean-out operation in Awi-4 has successfully reduced the NCG content in unit 4 and also added steam supply in Salak field. Thank you very much for your attention.
Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. I hope that you were safe and healthy during this pandemic time. First of all, let me introduce myself. My name is Muhammad Prasetya Dwi Aurianto, but please you can call me Pres. I recently finished my bachelor degree in Petroleum Engineering ITB this July actually. And I would like to say thank you to the committee for this opportunity. So today I will present the result of the study of my paper, Evaluation of Successful Metric Acidizing Method in Geothermal Well with Comparative Sensitivity of Acid Fluid Model, Volume, and Concentration, a case study on well X. I finished this paper with Mr. Dimas Tahamalana and Mr. Stephen Chandra. This is the outline of the presentation. Introduction, case study, methodology, result and discussion, and conclusion. Introduction consists of background of the field and history of metric acidizing. This paper was studied on well X as part of Ulumbu Geothermal Field located in Western Flores Island, East Nusa Tenggara, Indonesia. The field has been producing a total capacity of 10 megawatt, and it's a vapor-dominated underlying liquid-dominated reservoir with approximately 230 to 240 degrees Celsius. Previous study has indicated possible reserve of 100 megawatt electric and potential recoverable reserve at 150 megawatt electric. And it was observed that reservoir characterization of this field is a sandstone formation with quartz and silica dominated. Based on paper Yono, the field has a low permeability. And what will be reviewed further from this well is regarding the potential for formation damage around the wellbore, which usually occurs during well operation and has an impact on well productivity. Based on Cousin Papers 2019, the need for improvement on the performance of the well by eliminating formation damage using well stimulation. One of the well stimulation that is quite often used is the metric acidizing method, called metric because treatment in this method carry out below formation pressure so that fractures do not occur or are avoided. And this is the history of metric acidizing, or rather the fluid models that used in metric acidizing treatment over time. Started in 1895, which is believed to be the first time the stimulation work acidizing has been done. And it was carried out by Standard Oil Company, used concentrate ACL to stimulate oil wells producing in Lima, Ohio. And then in the late 1930 or early 1940, a new treatment was carried out with the fluid model introduced by Dawud, which is a mixture of 12% ACL and 3% HF called mud acid. In 1984, Harry MacLeod introduced a guideline in selecting an acid fluid model based on permeability and rock type, whose reference is from field experience. And after well stimulation has started in geothermal field, in 27 to 28, Calvayan on his books offer practical guidelines for acid treatment design with mixture acid of 10% ACL and 5% HF for geothermal wells with certain formation. And high HF concentration, which is 5% to 9% HF, has proven to be effective in geothermal well stimulation based on Abbott's paper. And this is the case study, consists of problem identification and objective. Determination of the fit zone in this well carried out by observing using well logging data, that is PTS flowing test, which is measured as shown in the picture. From the observation can be analyzed that this well has two fit zones. There is depth of 550 meters and 880 meters, or I call it upper fit zone and lower fit zone. And there is also a water level at depth of 600 meters. It can also be determined that the upper fit zone is the steam zone, while the lower fit zone is the water zone. Then when the flow test result is carried out, this well only produces dry steam which is read in the wellhead. No water is also produced as shown in the picture. My assumption is there is a flashing phenomenon in the liquid zone, so that when flashing occurs in the liquid zone, the liquid will turn into steam in the upper fit zone and produce dry steam in the wellhead. Based on the Abbott's paper 2007, one of the challenges of acidizing job in geothermal is relatively faster corrosive properties occurs. But in wells that only produce dry steam, the process of corrosion reaction will be much slower compared to wells that also produce water. So the well X can be categorized as a good candidate wells for an acidizing job based on corrosive properties, but other parameters need to be looked at. And one of the problem identification can be done by well testing analysis. There are three parameters. There are skin factor. If the skin value is positive, it indicates that there are formation damage in the well. The second one is productivity index. If value of actual PI is smaller than ideal PI after the calculation, it indicates that the well is not able to produce acid salts, probably because of formation damage. The last one is flow efficiency. If the flow efficiency is below 1, it shows that the permeability formation around boreholes shrink due to damage. In this study, there are three objectives based on analysis and evaluation with a numerical approach. from before, during treatment, and also after matrix acidizing. This study focuses on determining whether the well is a good candidate for acidizing or not, compare acid fluid model, volume, and concentration injected in matrix acidizing design, and then determine the acid design to get the optimum result of skin damage and fold of increase of the well. And this is the methodology, consists of flowchart. This study has been successful through several steps, as shown in the flowchart, starting with a literature study regarding matrix acidizing in general, and in particular in geothermal wells with sandstone dominance. Then preparation of data, which is very important in this study for input in calculation, design, and in doing simulation later. The next one is well performance analysis, is used to determine whether this well is a good candidate or not for acidizing job. And then based on sketcherbooks, wellbore profile calculation is also needed to perform matrix acidizing treatment. In this study, design a matrix acidizing consisting of an acid fluid models with the injection volume and concentration. Then a simulation of the acidizing matrix treatment is carried out on this well using software and Microsoft Excel calculation. After that, the simulation result from the software and Excel calculation are compared so that the result is which case is the most optimum seen from the decrease in skin factor and the highest FOI. And this is the result and discussion. This is the Harnett plot of the pressure build-up construct from the PTS-in graphic with the top-down method. That is from the wellhead to the bottom hole pressure. From this plot can be seen if well X is an infinite acting, and its logarithmic equation can be seen as shown in the picture. From this logarithmic equation can be determined the value of the slope, Harnett pressure at 1 hour, and reservoir pressure, which will later be used as input in the calculation of well testing. And this is the result of the calculation of well testing on the well X. Based on this result and analysis of this well testing, it can be concluded that well X is a good candidate for a matrix acidizing job. View from the value of skin factor is positive, productivity index actual is smaller than productivity index ideal, and flow efficiency is below 1. The next is wellbore analysis. In the acidizing fundamental book, Sketcher explained that to optimize the work of matrix acidizing in sandstone wells, design of the treatment must be specific not only the volume and type of the fluid, but it's also necessary to know the maximum injection, fracture gradient, and treatment pressure. This calculation is to avoid fracture in the formation when the matrix acidizing treatment is carried out. The result of this wellbore analysis calculation will be used as a parameter in the acidizing matrix simulation design. And this is the design of the matrix acidizing for comparing acid fluid model. Because in this study, we will compare recommended acid fluid model for matrix acidizing in sandstone formation that is commonly used in the field. The result is that 3 acid fluid models, including double models, McLeod models, and Calvin models, will be used along with same volume injection based on recommendation from Professor Jatirahmat, Literation, and from Sketcherbook. That is for cooling step is with 50 gallon per feet. Pre-flush step is with 75 gallon per feet. Main acid flush is with 100 gallon per feet. And for post-flush is done with 2 times greater from main acid flush, which is 200 gallon per feet. And furthermore, based on Sketcher and economy dash, for formation containing high concentration of clay mineral, normally require an acid containing HF to remove the formation damage caused by the clay mineral. As this well contain high concentration of silica, HF acid fluid is used as main acid by comparing its volume injection and concentration. All of these design are simulated by 2 stages because based on the literature that I read from Professor Jatirahmat and the book Production Enhancement with Acid Simulation Leonard Calvin, for wells with a temperature of more than 200 degrees Fahrenheit, which this well is 309 and 310 degrees Fahrenheit, need to do of 2 stages because stage 1 be set to eliminate formation damage, but also to lower the temperature from the well to below 200 degrees Fahrenheit, so that when stage 2 takes place, the result of the acidizing matrix will be more optimal. And this is the designing summary of the design model of the acidizing matrix in this study, which acid fluid model, concentration, and injection volume will be compared to find out which case the most optimum is used in this well X. After the simulation of acidizing matrix treatment has been done, here are the results obtained from the software and Excel calculation. From this result, it can be said that if the matrix acidizing job simulation in this well is 100% successful based on negative skin value and increased PI. Furthermore, need to be evaluated for performance during matrix acidizing to determine the most optimum case in the study. The first evaluation is when compares the acid fluid model that is commonly used in the field, which is a Dawud model, McLeod model, and Calvin model. If you look at the graph, the second stage of the Calvin model shows that the value of the skin factor has not decreased significantly. This is because, based on the economy dashbook, metric acidizing can reduce the skin factor and increase the productivity of the wells, when previously there was a formation damage. On the contrary, metric acidizing will have a minimal impact when the well has no formation damage. Based on that theory, my assumption is this well has completely safe for formation damage when the skin factor value is in the range of minus 0.5. In addition, it can be seen also that the greater the concentration of HF used in the model, the more optimal the result obtained. In this graph is the Calvin model with 5% HF. And it is confirmed when compared to the concentration and volume of another fluid model, that is HF acid. 9% HF acid shows more optimal result seen from the decrease in skin factor. Then it's the same with the previous Calvin model. Acid fluid 9% HF and 5% HF at a volume rate of 100 gallon per feet does not reduce the skin factor value significantly when the skin factor value is the range of minus 0.5. Then in the graph on the right, the value of 5% HF acid when the rate is reduced by half to 50 gallon per feet. It shows if the skin factor in this well has been successfully reduced to the range of minus 0.4 or rather minus 0.43. Besides skin factor, other results compared in this study are fold of increase. There is the ratio of PI before stimulation and after stimulation. Can be seen in the table, simulation of this well X succeeded in increasing the PI in each case. Other than that, can also be seen if 9% HF acid is the model that increased the PI with the highest value. And this is the graph, which if we compare skin factor and FOI value in each case. The results of the observation in this graph shows that the FOI value will increase in line with decrease in the skin factor value. This FOI value is also directly proportional with the productivity of this well, which means well production after the metric acidizing simulation will increase from 36.5% to 60%. And last, this is a summary of the result of the metric acidizing simulation in this well. It can be seen that 9% HF acid is the most optimal model seen from the skin factor and FOI value after the metric acidizing simulation is carried out. This is because 9% HF acid has the highest concentration of HF acid compared to other models based on McLeod papers and Dawud papers. In sandstone wells, HF acid is useful for reducing formation damage due to sandstone deposits, while ACL is useful for removing chemical composition such as calcite and will be reacting first, so that later HF acid can easily reduce formation damage in sandstone wells. In addition, it can also be concluded that the higher the injection volume, the more optimal the results will be. This can be seen from the 5% HF concentration, in which one of the volume is reduced by half, while the other is not. And this is the conclusion. My conclusion about this study is, first, geothermal well X with sandstone formation in this study is a good candidate for metric acidizing job on well performance based on well performance analysis and needs to do a metric acidizing job. Second one, comparing the metric acidizing design in this study has been done. Improvement acid fluid model result of skin factor and productivity index is sensitive to both acid volume and concentration injected. And the third one, the use of HF acid greatly affects the result of metric acidizing job in this well. This is because this geothermal well is a sandstone formation with quartz and silica dominated. So the use of HF acid is very suitable to reducing skin damage for this well. It is proven that 9% HF acid with 100 gallon per feet volume was the optimum case. And further improvement should be developed in the study to give more comprehensive result. The development can be done by first, create the design more cases than study does. This done so that there are more design models that determine the optimum cases for acidizing job in this well. Second one is more sensitivity on these acidizing jobs, such as drainage area, mineralogy, can be done to find out further about the effects of the sensitivity. And the last one is observe from an economical point in the future, such as net present value, can be done to make the result of this acidizing job in this well more comprehensively. And I will close this presentation with a sentence that has the same meaning as thank you, and it's from Sudanese, called